Alrighty, thank you everybody for joining. Today we're going to talk about the RAIDz on disk format and some interesting things I found when we're dealing with small blocks. So here's the agenda, I won't read it. First of all, here's some terminology that I'll try to stick to because in particular there's some it's easy to get confused between sectors on a disk or blocks on a disk and blocks at a higher level. So whenever I'm talking about a block on a disk, I'll try to call that a sector. A block will then be an allocation at some higher level at ZFS or perhaps in a volume or at a in a database. Databases commonly call it a page size. ZFS has a couple names for blocks. When dealing with a ZFS file system, it's record size. When dealing with a volume, it's vol block size. Also, a lot of people equate the term dataset as a ZFS file system, but dataset is a generic term that covers other objects like volumes and snapshots. And here, when I talk about dataset, I'll either be talking about a file system or volume. So how did we get here? We had a customer support call with somebody that was using RAIDz 2 and had a bhyve VM that ran out of space. And it was kind of confusing because we take special care to be sure that we set the quotas and reservations and such that you can't run out of space. It turns out that there's a bug in the way that ref reservation is set with RAIDz, and that covers RAIDz 2 and RAIDz 3 as well. Whenever I say RAIDz, I mean all three of them. And so it was not reserving all of the blocks that are actually allocated, and there's air quotes around all of the blocks there. This gets very complicated. So as I was looking into this, I realized that anytime that you have vol block size that is less than about 4 times the disk sector size, you have a tremendous amount of overhead. So RAIDz turns out to require about as much space as mirroring. RAIDz 2 requires about as much space as triple mirroring. And you can guess where that goes with RAIDz 3. This comes about because the way that disk drives are working is changing. And I say disk drives, I mean that in a generic term. So this covers flash-based storage like NVMe and SSDs, as well as traditional hard disk drives. So in the old days, all disks were 512 byte sectors. That's not exactly true. There's other forms that have higher redundancy and such. And in the very old days, it was a different size. But the drive that you have sitting in your drawer somewhere is probably has a 512 byte sector. As we get into larger and larger hard drives, that is changing so that all drives have 4K sectors. So random Google search turned up this UltraStar disk, looking through its data sheet, which is linked there. It says that it has 4K sectors, so known as a 4KN or 4K native disk. The old drives are known as 512N, and a drive that really has a 4K native size but can emulate 512 byte sectors will be referred to as 512E. If you want to know the motivation behind all this, follow the link at the bottom of the page. It provides a great overview. So we care about block size kind of matching sector size because we're worried about I/O inflation. When you have IOs that are not aligned with the underlying sectors or smaller than the sectors, that means that you're doing more physical I/O than what you might expect. So when we're talking about VMs running on top of SmartOS, most of the guests are going to be running Linux or Windows, and those file systems tend to default to using 4K blocks. If we're talking containers and potentially other uses, we'll have potentially have databases running natively. So Postgres, for example, not so much Oracle, perhaps SQLite. Postgres and Oracle have a default page size, they call it. Oracle might call it block size, I forget, of 8K. SQLite defaults to 1K. So if you're doing a whole bunch of I/O on those with 128K file system block size, you're probably going to have a whole lot of I/O inflation. It gets particularly bad when you have a read modify, when you have a write, because that turns into read modify write cycle. You have to read all the data to be able to calculate the checksum and parity, and this applies to ZFS blocks too. So if it's not just at the disk sector size, if you're trying to read a part of a ZFS block, you have to read the entire thing to be able to calculate the checksum. And if you are writing, you have to be able to calculate the checksum and be able to calculate parity if you're writing off to RAIDz. So by default, when you provision a compute node, the pool configuration is chosen by disklayout.js. Pretty obvious what happens with a single disk. If there are fewer than 16 disks, it defaults to a two-way mirror. Otherwise, it goes to RAIDz 2. And the smallest block size that ZFS will use is based upon the makeup of the disks in the pool. So if you have even a single disk that's a 4KN disk, you're going to end up with A shift equals 12. 2 to the 12th equals 4K. So if you have a pool with A shift equals 9, it's not possible to add a 4KN disk. It may be possible to add a 512E disk with a patch that's floating around. There's code review for it, but it hasn't been integrated. So file systems generally use 128K record size. Volumes generally use an 8K vol block size. Some of our images, I believe in particular the Ubuntu images, may use a 4K vol block size. And as I mentioned earlier, the reason that we got into this discussion was because bhyve tries hard to be sure that we have enough space reserved and that we're not able to use more space via a whole bunch of snapshots, for instance. Plenty of details in this are in RFD 154. There's also RFD 148, which has a document snapspace.md, which is actually a link from RFD 154. So RAIDz block allocation. Since we're really concerned about what's happening on 4KN disks, all of my examples are with 4KN disks. Here I show the disk sectors across 5 drives that are involved in a write of 128K block. So we have 8 blocks that are used, or I'm sorry, 8 sectors that are used for parity and 32 sectors that are used for data, for a total allocation size of 160K. That means that the pool's alloc or allocated will increase by 160K with this write, and the available will decrease by, I'm sorry, free in the pool for the pool property will decrease by 160K. The dataset referenced value will only increase by 128K. So ZFS has this notion that 128K block is the typical size, and it will charge the reserved property on a data set based upon how much space is being used relative to how much space to be used for 128K blocks using the same disk layout. That's confusing. We'll get into that a little bit more shortly. So RAIDz is not like RAID 5 when it comes to blocks that are smaller than a stripe width. it calculates parity on a per block basis. So when your block size matches your sector size, that means that you have a parity block for your block for every data block. So in this case, we wind up with, when you have 4K blocks on 4K disks, that you wind up with using as much space as you would if you were mirroring. So this 160K of disk space can consume 80K of data. You know, with our typical image size of 10 gigabytes, that means that that we actually need 16 gig to be able to store this. And that's 16 gig plus the normal RAIDz overhead, so add another 25% on that. So we're really using 20 gig for a 5-disk pool with 1 disk of parity. So that is equivalent to if we're using mirroring. When we get up to 8K, we run into another surprising feature of RAIDz, and that is that it does all of its allocations on a multiple of number of parity disks plus 1. So when we're trying to write an 8K block to a 4K disk, we need to have 1 parity block plus 2 data blocks. That's 3. That's not a multiple of 1 plus 1. So we add a skip block. And so you'll notice here with 8K that we wind up using the same amount of space, same amount of physical disk space to store at 8K as we did at 4K, because now we're allocating a skip block, or really a skip sector in the terms that we're using in here. In the ZFS code, you'll see it as skip block. So this has a little bit of an advantage over 4K in that we only need half as much space for metadata, but the size of metadata is really quite small compared to the size of data, so it's really not that big of a deal. But when we have a file system sitting on top of this in a VM, for instance, and it's running some random workload that has 4K IOs, you're going to run into the IO inflation problem I talked about earlier. If we skip ahead to RAIDz with 32K blocks, things in this particular pool layout just happen to fall into place so that we're just as efficient as 128K. That's great. But if we add more disks, then things don't line up quite as well, and we have a little bit more overhead than we do with 128K. But generally, as we get larger block sizes, the more efficient we are. So this table here shows the relative overhead of the various block sizes and RAIDz1 layouts. This is based upon actual measurements of creating a Z-vol, filling it up, and seeing how much space it takes. And so these numbers are all relative to how much space would be used for with 128K blocks. It does not account for the additional parity disk that's in there, so you need to increase this a little bit. If you're looking at how much space do I need to store a whole bunch of 4K blocks, it's not 1.6 times the size of the volumes, it's actually 2 times the size of the volumes in the RAIDz with 5 disks case. So I've been talking for a while. Does any of this sound confusing yet?
No.
All right. If anybody else has a different opinion, speak up. So RAIDz 2, kind of the same story. I've added a disk here, added another parity disk here rather than reducing the number of data disks. We now need 192K for storing 160K. We charge reference to 160K, and the pool's alloc and free change by 192K. Triple mirroring, if you were to do the exercise on your own, you probably would have wound up at this pretty quickly. I'm sorry, with the 4K block, it winds up looking a lot like triple mirroring because you have two parity blocks for each data block. Now, if you're going to do this, you just as well do triple mirroring because you're going to have a similar ability of withstanding failures. And you'll
have a drastically different capacity.
What's that?
You'll have a drastically different capacity.
Well, if you're only writing 4K blocks, you're going to have the same capacity. If you have a whole bunch of blocks that are, if a significant part of your pool is filled with things that can actually use larger blocks, you're absolutely right. Your RAIDz 2 can be more efficient. This right here is the point I'm trying to drive home with this presentation, is that if you have a pool that is primarily storing bhyve VMs or KVM VMs with 4K, and as you'll see on the next slide, 8K blocks, the amount of space that you're actually consuming is equivalent to triple mirroring. So the 8K block example, the skip blocks come into play one more time, and we see that we wind up having two skip blocks, two data blocks, and two parity blocks for every 8K. So not a good situation again. The 16K is a much better situation. Here we're at the equivalents where we were at with the 32K on RAIDz 1, just because everything falls into place such that we're allocating just as much parity for the parity to disk ratio is the same, and there are no skip blocks. But as your RAIDz 2 stripes get wider, you wind up with a bit less efficiency in some cases, and that is outlined here. So the same exercise, just changed from RAIDz to RAIDz 2, and again, you need to this is just the relative factor compared to the amount of space used for 128K blocks. You need to, if you're looking at the overall space that's used, you need to adjust for that. So what are we doing? I've been working on Illumos 9318 to make it so that the ref reservation equals auto. That is actually the Illumos version of the fix for OS 7824. I just worked it in Illumos, so it's easier to get some of the ZFS folks to outside of the company to take a look at it. And so that should be landing in the next couple days. Right now, skip blocks are only accounted for at the accounted for in a roundabout way at a SPA level, but I believe that would also be possible to be able to keep track of that at the dataset level. It might be useful for doing that. It would be particularly informative in cases where we're using compression, where it's not just a simple matter of looking at the block size and the volume size or the amount of space used by the file system and doing math on it. Whether that really helps anybody other than understanding what's going on here without having to look at this presentation, who knows. There's also a successor to RAIDz coming along called DRAID. We might want to look at that to see if there are things in that already address this. In particular, maybe it can avoid the skip blocks. That would be a big help in a lot of cases. We might also want to take a look at the way that we're doing our default pool layout. So if the pool has an A shift equals 12, then maybe we want to always default to mirroring. it's worth a discussion. And this is not relevant just to bhyve and KVM, but also if we're running large Postgres databases with record size set to something kind of small, we could be having the exact same problems. And if there's some file systems that have something that's storing a lot of really small files, but not 125 or 112 bytes or smaller, then mirroring may be a benefit as well. 112 bytes is the magical amount that can be stored in a block pointer, and avoid allocating the data block. I think this is something that we need to include in documentation around bhyve deployments to ensure that people understand that if they are expecting X terabytes of space to be usable by their VMs, that there are some special oddities with RAIDz. It also comes into play with flexible disk space, where people may need to allocate more space to their VM than what they would normally expect. I think it's also reasonable to explore just using a larger block size by default. We may run into more read, modify, write cycles. Delphix has explored this quite a bit with running Oracle databases on top of ZFS. And they found that using compression, even with the potential for I/O inflation, is a win. I'm not sure how much of that was with 4K-N versus 512N. So
So a couple things. I mean, there are no 512N drives anymore, basically.
Yeah.
So it's clear. And then the other thing is that the read, modify, write depends a lot on the performance of your I/O subsystem and how much of that is cached.
Yep.
Right.
Exactly.
If you look at the Postgres databases that we had in Manta, because they were disk I/O bound on the HDDs, it didn't matter if you were doing the read, modify, write, even with compression, it still hurts. So
right.
Other thing is, have we looked at actually changing what the guest uses? Like, what about we change the guests to actually look at using a larger block size?
Right. Well, it's not just what size the guest is using. We need to change the volume size.
Sure. Right. The two in tandem. I'm just saying, like, have we looked at actually getting the guest to know? I mean, the Vert.io block, and presumably with Vert.io SCSI, you can actually change what that looks like, especially as SSDs are looking to increasingly larger block sizes as they go on. So 4K today, but I would not expect that to be the end. Some vendors are already talking about doing 16K block sizes on SSDs.
Right. Yeah, and I believe I've seen some already where they're saying 8K is the native internal, but
right, but those aren't exposed. So I'm just talking about ones where they actually are talking about exposing it. So you'd actually have a 16K physical block size in the SCSI headers or NVMe headers. So just trying to they're trying to think about that.
Yeah, at a previous job, I ran into a customer request for ZFS supporting a shift equals 14 for the 16K blocks that their array was presenting several years ago. So, and so even if we're like today, where we have 4K blocks or 8K blocks exposed at the host level, if we have a database running inside it that's at the 8K block, it could align those 8K blocks such that it's not actually on aligned with the 8K block underneath. So we wind up with I/O inflation because of that. So having the knowledge of the geometry all through the stack presented all the way to the consumer is can have some benefits. And it definitely deserves an investigation as to how much of that is available in Vert.io and Vert.io SCSI, Vert.io block and Vert.io SCSI.
Well, for SCSI, you just change you just reply with a different SCSI
Right, with the
command.
block size versus.
For Verdeo block, I'm fairly certain that's been in there for years.
Yeah. And if we're addressing this for making changes that are aimed at RAIDz, we need to keep in mind that as images are used across RAIDz and mirror pools, the block size follows the send stream. So sending it to a different pool that has different characteristics does not change the block size that's used. And this also goes for migration. And in the case of migration, if you're migrating from a mirrored pool to a RAIDz pool, you can wind up finding out that you're using more space than what you used to, or you may be using the exact same amount of space as what you're using. The way it's counted will be different, and appears that you're using more. And we started to discuss a little bit early. That's okay. Any other questions or comments? And some follow-up reading. So the first link was really the thing that first helped me to understand how this was working. That was followed by quite a bit of discussion with Richard Elling and a little bit with Matt Ahrens. Thank them very much for being patient with me there. The big theory comment is actually right here. So if you want the short version of this presentation with the background that you now have, you should be able to figure out this comment. And that should be in libzfsdataset.c shortly. Last chance for questions. Alrighty. Thank you, everybody. Oh, and also a thank you to Jerry and Cody for their code reviews on the fix.
Thanks, Mike.
All right.
Thanks, Mike.
Bye.